Hello everyone. I appreciate the opportunity to share my work here. My name is Luca from Huazhong University of Science and Technology. The title of my presentation is ADSTS, Automatic Distributed Storage Tuning System using Deep Reinforcement Learning. There are four parts in my presentation. The background is first part. For modern distributed storage system, performance tuning is an important but difficult task. Supplier configuration setting can provide significant gains in performance and high quality of service. With explosive growth of data emergence, distributed storage system has the following characteristics which bring more challenges to determine the optimal configurations. First of all, much parameter space in distributed storage system. There are hundreds or even thousands of tunable parameters and control. For example, distributed storage system self comes with 1,536 parameters in the latest version, nearly 3 times larger than the original version. Secondly, the parameter can take on a wide variety of values, whereas those parameters have many value constraints. Thirdly, in a model storage environment, workloads are often dynamic and unpredictable due to the large number of users and data. Finally, evaluation is time-consuming and the results often contain static noisy in distributed environments. In recent years, there are many researchers on automatic tuning of storage systems, including search-based and learning-based. An ideal auto-tuning system can automatically adjust all parameter values for optimal performance based on the current workload. Among the existing schemes, reinforcement learning-based auto-tuning schemes show excellent performance and are used widely in the database field. While it is still in the explorator stage for distributed storage system, CAPS is the state-of-the-art RL-based auto-tuning system. CAPS adopts DQ model and only tunes 2 parameters in distributed field system last year. We found that RL-based auto-tuning systems like CAPS have several limitations when actually running. The first is limited performance improvements. The experimental results show that CAPS performs well on workload A but performs best on other workloads. The local optimistic results and poor adaptability are caused by 2 reasons. One, DQN is not suitable for real-world continuous parameter. To use DQN, parameter value are decreased size and tune step size is set, which results in limited parameter value. In addition, lack of parameter identification and the process needs to optimal performance. The second is poor availability. First, the time-consuming training of RL model inspired training for 24 hours. The performance improves the little compared to 12 hours. The model conversion is hard to encapsulate, especially when there is a large amount of tuning parameter. In addition, it needs to change the target system to use CAPS, which is inconvenient for users and has poor probability. So it needs a more efficient auto-tuning strategy for modern strategy systems. We provide a solution, ADSTS. The ADSTS is designed to be non-invasive and work with many storage systems. This figure shows the architecture of ADSTS, which consists of 4 main parts. Common interface is the canonical request or responsible interface between ADSTS and the target distributed storage system. Metric collector is responsible for collecting the system state and performance data from the system. This metric are sent to the tuning agent as a state and reward information. Action controller apply recommended configuration suggested by the tuning agent. Memory pools store the neutral network parameter and the experiments replay memory called replay buffer. The buffer is used to store state, action, reward cycle, and tuning agent. Parameter processor is responsible for getting and processing the complete parameter list according to user setting and identify important parameter. Afterwards, processor generates a standardized configurable parameter list for later tuning process. Tuning agent, which receives reward and state from interference and updates the process to guide how to adjust the parameter and the parameter list for getting higher reward. The parameter complex in the distributed storage system can be summarized into four categories. Constraint 1, C1 for short. Some parameters are configurable. C2, some have strict boundary. C3, some parameters determine whether other take efforts. For example, Ceph provides boot store and file store as two different store backends, and use parameter OST object store to determine which to use. C4. Some parameter values are interdependent, like they must have a fixed sum or one must lower than the other. To solve these constraints, the processing guidelines is processed and can be divided into three steps. Parameter prompt, getting the complete parameter list and remove the untunable parameter to C1, C3. Parameter processing normalize the value of all parameter and set up the value boundary to C2, C4. Parameter identify subhead parameter space and identify important parameters. ADSTS obtains the complete parameter set through system document and all source code. Based on the model hierarchy of the storage system, ADSTS builds a tree-based indexing structure called model tree. Each tree node is the name of each model or submodel. In the model tree, ADSTS first includes the configurable nodes C1, such as the strict hardware module. In addition, some modules are not used for the specific user case C3. In the example, one blue store is used. All parameters about the file store submodule will not be used. ADSTS will remove this unused module according to the user setting. After parameter cloning, all tunable models are arranged into the module tree. In ADSTS, the parameter is arranged as an entry with 6 attribute model type default range boundary, which means the parameter name. The module belongs to the type of value, the default value, the value range, and the boundary type. For each parameter, the standard process follow is as following. First, look up the model in the module tree if root found delete parameter. Second, process data based on the type. For the long numerous value, including boolean, or categories, ADSTS will convert them to numbers by mapping candidate values to consecutive indexes. Set up parameter bundle with range for dependent parameter sequel. The range is equal to the fixed development a dependent value range. For boundary parameter C2, the range is equal to specific range. The boundary type of these two kinds of parameters are set to static. Unfortunately, most parameter values have no clear boundary. ADSTS sets the through parameter range based on default value and adopts a dynamic boundary approach, which will be describe the nature. ADSTS dynamic enlarges the extent of parameter when the probing point come near the boundary. The boundary attribute is level dynamic. An example entry is like this. After parameter processing, ADSTS gets a list of tunable parameter entries. Next, the workflow of the parameter identity consists of 3 steps. First, shuffle off the entire parameter space. However, traditional shuffle algorithm, including the suffice subholding are not suitable for our problem because they begin with a fixed state size and the code that is incremental nature. So in ADSTS, recursive stratified subholding RSS for short is proposed. Second, probe the target storage system with this subhold configuration and complete system performance data. Third, identify important parameter based on the feature selection algorithm, or choose the efficient lattice regression. The RSS states are recursive combined from pairs of RSS or SS set up with sets with equal sacrifice subspace. The top sample set 1.1 can be viewed as second sequence of samples. Take the boundary RSS set generation as example. The initial is sacrificed subnet as state. Any pi set is combined from the two smaller sets pi I and pi j with the random max tree set. RSS sequence are conditional of RSS subsequence. Therefore, RSS can be expanded even by any sub from a large RSS sequence to an initial RSS subsequence. RSS is extensible without the non-incremental nature. Next, we introduce the tuning agent. We choose a certain number default tuning rule and secondary system status and state metrics. Example rule status include buffer size, CPU utilize, etc. and secondary system status include data rate and the number of active threads, etc. Action dictates what K parameter is parameter needs to should be. The action of each parameter has three options to increase or decrease value of any size or no action. The parameter value cannot exceed the space range. If boundary exceeds the limit, the value cannot exceed 10% of the upper limit. Such a dynamic approach facilitates the search for optimal states. Reward is the performance changing after the system performs the new configuration commanded. ADSTS choose TD3 model. TD3 is an extra critical algorithm. The extra network outputs the place mapping the state to the value of action. The critical network aims to represent the value with specific action and the state for guiding the learning of action. TD3 uses 2Q network to estimate critical network with the small one as the update target. Multiple processing training is adopted to speed up training process by connecting experience to the parallel. In each approach, the main process performs the GD3 training task. After getting the network of the main process, several child processes are created to explore the environment in parallel to collect more precision. On the other hand, we found that optimal configuration based on the same type of workload are close, as the module has the same parameter. According to this discovery, three base models are trained once offline with three workloads: read intensive, write intensive, and the read-write mix. If the approximate workload type of the user is known, the tuning model is initialized using the corresponding base model. Then ADSTS replaces the user's current workloads to control stress testing on the target system in order to fine-tune model. Model fine-tuning method is used in a more complex case. When the user wants to monitor more system metrics or adjust more parameter value. In this case, input-output dimension of the model will change when the dimension of the neutral network increases. The parameter of the old model will be used as initial parameters of the lower dimension of the new model, and the new dimension will be zeroed or randomly initialized. In this way, the training speed of the new model will be generally increased, or even increased by hundreds or thousands of times. The next is the evaluation results. ADSTS is successfully packaged into the actual distributed storage system. SAFE 12.2.13 version with 1,384 parameters. The SAFE environment is conducted on 5 hosts, including one monitor host, one client host, and 3 OSD hosts. Each host is equipped with this hardware. All experiments are run on the client host, and a GPU device is used to train models. The experiments are conducted using the three kinds of benchmark tools: random bench, released with caps, post bench. Three workloads is a benchmarking tool to measure the performance of distributed object storage service, and the YCSB on step 6 workloads. We compare ADSTS with 4 strategies. The default use the default parameter of SAFE. The SAFE file is auto-tuning systems for SAFE using ISA optimization. Load then the SAFE file process the parameter space and select 16K parameter. The RFGA adopts random forest and genetic algorithm to automatically tune SAFE. It selects specific 7 parameter. The caps only tune 2 parameter use DQ1. The experiments are divided into training and tuning process to be fair. All systems are firstly constructed based on the random range for training. and the final turned under different workloads for tuning. The training process stops until the model converges or the performance does not change. Performance evaluation is the tuning process. We first compare the overall performance of the system based on random bench. The random bench including sequence write, sequence read, and random read operations. This figure shows the throughout throughput IOPS and average net sale helps use configurations recommended by three strategists under different operations. The results show that ADSTS performance-based, which boosts the write performance to about 1.5 times and the read performance to about 2 times with lower latency compared to the defense. The adaptability of this system is compared using YCSB and the COS bench. The last student ADSTS has good adaptability via workloads. In COS bench workloads, ADSTS significantly boosts staff performance to 1.5 times to 2.5 times compared to other strategies. ADSTS outperformance developed by 1.58 to 2.2 times on all the YCSB's workload. The overhead is measured with average runtime and system resource use. The runtime is measured from the start of tuning or stable performance, including the tuning time for the training process and the implementation time for tuning process. The results show that RFGA has the short time runtime because RFGA only needs to calculate the performance model instead of running the test. Tests take a long time to train AI model while ADSTS speeds up the training process through optimization. In addition, this system can complete parameter recommendation for new workloads in less than 10 times. In addition, ADSTS and RFGA make better use of GPU and CPU resource in general. CAPS and ADSTS have the most memory consumption for replay buffer. In conclusion, ADSTS require more CPU, GPU, memory resource to ensure excellent performance. But these resources are acceptable compared to existing resources. In this section, we evaluate the efforts of parameter processing and training optimization. With the processing guidelines, ADSTS reflects the importance of storage parameter using lasso. The finger indicates that some parameter can significantly affect performance than others based on the ranking. The top set of parameters are selected in addition. We tested ADSTS with top 16, 32, 64, and all parameter and collect the performance every hour. None means no parameter processing. ADSTS without parameter processing has not converged after more than 7 hours. ADSTS needs more about 6 hours to reach optimal configuration use of parameter, while with the top 32 parameter ADSTS use only 2 hours. In summary, ADSTS can identify the most important parameter by the processing guidelines to shrink the optimized time. Moreover, the number of important parameters needs to be chosen carefully. Too many parameters may increase time overhead, while few may need to poor results. For training optimization, these results show that the ADSTS has less error and the training time is lower than common training through multi-process training and model fine-tuning. The last part is the conclusion storage system with the immense number of configurations, unpredictable workload, and difficult performance evaluation pose higher requirements to parameter tuning. Several researchers adopt deep reinforcement learning to automatically tune parameter setting. But there are many limitations, including lack of parameter space, processing, less advanced model, and time-consuming training. In this paper, we present ADSTS, which addresses this problem with the three technologies. Firstly, ADSTS processes a general parameter to processing guideline to identify the key parameters that most affect performance. In addition, ADSTS utilizes TD3 algorithm to find the optimal configuration in high-dimensional continuous space. Finally, ADSTS adopts multiple processing training and model fine-tuning to speed up the training. ADSTS is used in the real-world distributed storage system SIP, and the evolution shows ADSTS outperformance significantly other existing auto-tuning strategies with acceptable overheads.